So now next topic is the reverse trace design for finite and infinite life. This is also interesting topic. Let's see it. Now reverse trace design for finite and infinite life. We all know there are two types of problems in fatigue design. That is components subjected to completely reverse traces and the components subjected to fluctuating stresses. In reverse traces, we know that the mean stress is zero. So the component can be partially tensile and partially compressive. This is we can see here. This can be tensile, this can be compressive. But in fluctuating stresses, what happens? The mean stress is not zero. So what happens here? The stresses can be pure tensile or purely compressive. Or you can have the mix of tensile and compressive. It depends upon the magnitude of the mean stress. So which is explained in the next section also much more detail. So in design problems, what happens? For completely reverse stresses, because we are studying here the reverse stress topic for finite and infinite life, it is further divided into two types, in two groups also, that is infinite life and the finite life. Now let's see for the infinite life. When the component is subject to design for infinite life, what happens? The endurance limit becomes the criterion of failure here. So based on that we are going to design. So the amplitude stress induced in such component should be lower than the endurance limit. So it is designed with the help of this equation, that is sigma A is equal to SE upon factor of safety and shear stress is SSE upon factor of safety. I hope you remember that SE and SSE, okay, the amplitude in the component and SE and SSE are corrected endurance limit in reverse bending and torsion respectively. So now for the finite life, this is for the previous slide was the infinite life. For finite life the equation somewhat different and somewhat lengthier also. So when the component is subject to design for finite life, the SN curve shown here can be used. This is the SN curve, okay, this is N and this is for the S direction. So this is the line AB. Let's see how it has been developed. So the curve is valid for steel only. Now it consists of a straight line here. Straight line is shown here, that is AB, which is drawn from zero point 0.9 SUT at 10 to the power 3 cycle. This is 10 to the power 3 cycle and zero point 0.9 times the SUT. This is the SUT. Yeah? So from here it is drawn and till what? Till to SE at 10 to the power 6 cycle. So 10 to the power 6 cycle, and this is the value of your endurance limit. This is 0.9 SUT and this is the endurance limit value on a log paper. Now the design procedure for such problem is as follows. Firstly, locate a point A with coordinates 3, log to the base 10.9 SUT. So based on this we have did. Then locate point B, as I told you, that 10 to the power 6 cycle and log to the base 10 SE, which is shown here. This is 10 to the log to the base 10 SE and this is 10 to the power 6, or you can say 6. Now join this AB line, okay, for finite life problem, and draw a vertical line passing through log to the base 10 N. Now draw the line FE parallel to the abscissa. Okay, abscissa means your x-axis. This we have drawn a parallel line here. Now the ordinates at point E, the ordinates at point E, that is log to the base 10 SF, give the fatigue strength corresponding to N cycle. This is the fatigue strength. After this it can get a failure value. So the value of fatigue strength obtained by this above procedure is used for the design calculation. So this is how the finite life design can be done. So this value of F is used for designing the component. I hope you understand this part. Thank you.